कैसा है ब्रो? बढ़िया। मस्त लग रहा है भाई। इतने दिनों बाद 10 बजे से स्टार्ट हो जाएगा। हाँ। Good morning, students. Am I audible? Okay, guys. Uh, I need you to just let me know if my voice is clear and the screen, if you're able to see me writing. Yes. You can use the chat, say hi, or just let me know. Mm, 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 mm. Okay, guys. So last time we had discussed heat transfer, and that was the end of thermal properties and matter. In heat transfer, we basically understood that heat transfer happens in three different types. One is the conduction, the other is the convection, and the last one is radiation. The mechanics of all these three types of transfer were different from one another. As in case of conduction, you had dq by dt dependent on the temperature difference, the something called the conductivity, and also like the length and the area of the conductor you're using, and all that stuff. Today we will be continuing with something called the thermodynamics, which you have already studied in your chemistry subject. And yeah, we'll be understanding thermodynamics from a different, but slightly different perspective. At the end of the day, the basic laws of thermodynamics are not changing. Just because we are studying thermodynamics in a different subject, that doesn't mean that something has changed. It's essentially the same value, the same topic, same uh, subject matter. It's just that the perspective is different. Uh, so that means there are some conventions in science. For example, somewhere you'll take positive in chemistry, that same thing you will have to take negative in physics. So it's just a matter of perspective. Other than that, everything, the basic, zeroth law, first law, second law, they are universal. It's not dependent on the subject. So without further ado, let us start with the basics of this chapter, right? So I think you already know what thermodynamics is. Okay. It's essentially a branch that lets you study between the relationships between three things. Okay. Now let me list those down. So the relationships between heat, and then there is work, and then there is energy. Okay. So what is the relationships between heat, work, and energy? Okay. That branch of physics which talks about this is known as thermodynamics. Now, what's happening is you are seeing this as one chapter as of now. But as you go into engineering, guys, you will find that thermodynamics in itself becomes like a subject of its own. It's that big. And to be honest, the significance of thermodynamics is it's from the smallest to the biggest thing. So if you have a cup of tea, uh, to the biggest engines that you're making for the planes or anything, a in-depth knowledge about the thermodynamic aspects of the body will be very, very important. So that is essentially the scope of this chapter, where the in terms of application wise, it's insane, right? So everything around us will sort of be part of or be a part of thermodynamics. Yeah, to be honest, it's part of thermodynamics. So that's why studying this chapter is like immensely important. The understanding behind it is very, very important. Okay. Now, recently, few things regarding the chapter has been deleted in JEE Mains that involves the engine and all that stuff, like the Carnot engine and stuff are deleted from JEE Mains. But JEE Advanced syllabus has also come, and their Carnot engine is there. So, as part of discussion, we will take up the deleted segments as well. Because it may be deleted from JEE Mains, but it is still a part of JEE Advanced, so it is my duty to let you know which part. I'll let you know it's a small part that got deleted from the CBSE and the NCR and the corresponding JEE Mains exam, right? But otherwise, this chapter is going to be a cruise. It's not that difficult. Calculation wise, if you understand the basics of this, you're going to love the topic. Okay. So here I'm just collating some pictures where I'm telling you that this particular chapter, thermodynamics, it's very relevant. It's sort of everywhere. Okay, starting from engines, the most complex engines, to a cup of tea, you have to understand what thermodynamics is. Okay, so that is the idea here. So basically, that was my introduction to this chapter. The branch of science which deals with heat, work, energy, the relationships between them, is known as thermodynamics. But anyway, the next important thing before we start the chapter is the knowledge of the fact on what exactly the system surrounding and a boundary is, right? Uh, so what can I say? So thermodynamics is not concerned like the thing is that with up to this point you have studied a lot of classical mechanics, starting from kinematics, rotational motion, and then fluid mechanics and all that stuff. But you have to understand key thermodynamics is slightly different from those chapters in the sense that it's not concerned with the motion of the system as a whole. Okay, it is concerned with the I want to say something like the internal state or the internal macroscopic state of the body, right? So it's all about what's happening inside the system or inside the body. So and to effectively study that, you have to categorize everything properly. So whatever properties you are studying for the subject that's under your microscope is known as system, right? So we are studying essentially I just said that thermodynamics is the study of heat, energy, and work. So whatever internal energy is happening, it's part of the system. That means if I write it very simply, then system is this is the part of the universe which is under study, right? And what exactly is surrounding? Surrounding will be something like everything in the universe except system. right? Now, again, pretty much common sense this is. What exactly is boundary? It's essentially the interface. This is the interface between system and surrounding. Okay. Now, this boundary, now, it can be of two types. Okay. I don't know if you have heard about these terms before. If you have, please feel free to let us know. One is adiabatic. Now, what is we just discussed that boundary is like the interface between the system and surrounding, and a very acute knowledge of what exactly the boundary is for a system is going to be important in this study. Okay. So now boundaries are of basically two types. One is known as the adiabatic walls, and the second type is diathermic walls. Okay. Someone who has studied this in chemistry, can you please let me know what exactly are adiabatic walls and diathermic walls? Please let me know. What do you think, Purva? Purva, are you there? Do we have any idea on what adiabatic walls and diathermic walls are? What about, yeah, Purva, please let me know in the chat. Unable to unmute. It's okay. It's okay. You can just type it. What is adiabatic walls and what is diathermic walls? It is okay if you're unable to unmute. Kind of forgot. Cool, cool. It works. But let me remind you on what exactly adiabatic walls are. Uh, Adiabatic walls are something like which does not allow for heat to transfer, right? So if you have uh, a cup of tea and your cup of tea is essentially the tea inside your cup is essentially the system. The atmosphere around the tea is the surrounding. Now if you keep the tea for some long time, the tea cools down. That's because heat got transferred from tea to the surrounding, and that is only possible because the boundary that we are dealing with, the cup that you are using has diathermic walls, because it allows for this allows for heat transfer, right? Something like adiabatic walls, the heat transfer would be zero. Okay, so that is the meaning of the boundaries, adiabatic and diathermal walls. Please note that down if you don't remember, right? So this is the basic idea. Now, one thing again, one more thing that because you have already studied uh, thermodynamics in a different subject, I have to debunk a few myths. Okay, and I don't know how many of you, uh, you know, have these myths, but if you do, then I'll help you debunk them first. Okay, so when we talk about thermodynamics, okay, there are the five thermodynamic variables, like this. Five thermodynamic variables that I have to work with. Okay. Namely, pressure, volume, temperature, internal energy, and entropy. These are the five thermodynamic variables that we'll be talking about. Okay. Some basic things about these variables is some of these are known as state functions. Okay. And what is the meaning of state functions? These are essentially those uh, functions which are, or those variables which are essentially independent of the path, right? So it doesn't really matter what kind of process it underwent. It's like work done by a conservative force is independent of the path. Something similar to that. So state functions similarly will essentially have scenarios jahan pe the final, if you want to find out what is the state change in a state function, that's good. State function, you have to find out what is your final state and what is your initial state, and then you subtract them both. It does not depend on what happened in between. It could have gone through a adiabatic process or isothermal process or isobaric process, any other process. This particular, if something is a state function, then it will be, now give me an example. Out of these five, internal energy is something that is a state function, right? Which does not depend on the process. Okay, and we'll talk further into this. But these are the five thermodynamic variables that I'm working with in this chapter. Okay, so whenever you're talking about the thermodynamic variables, these are the five variables that are of concern. That are of concern. Okay, so everything around thermodynamics will be happening. If we have an idea for these five variables, we know everything about that process. Okay. Now, when I say thermodynamic equilibrium, guys, there is this misunderstanding that if I say thermodynamic equilibrium and there is thermal equilibrium, what is the difference between the two? If I say thermodynamic equilibrium and I say thermal equilibrium, what is the difference between the two? Okay, so you gotta understand if I say thermodynamic equilibrium, it means all these five variables are constant. Okay, all these five variables, pressure, temperature, volume, entropy, and internal energy, all of them are constant. Then you say thermodynamic equilibrium. Thermal equilibrium, on the other hand, is where temperature is constant. Okay, so I hope you understand this one. Sometimes when I say thermodynamic equilibrium, people misunderstand it to be thermal equilibrium, right? But thermal equilibrium is very, very limited. It's only talking about temperature being constant. Whereas thermodynamic equilibrium is like a superset where you're saying all the variables that define thermodynamics are at are at values which are pretty much constant. Okay, so that is something that I wanted to say is slightly different from what people misunderstand. Okay, so before we start the first law, there is something called a zeroth law. Okay, now what is zeroth law of thermodynamics? Pretty simple, very, very simple. Okay, now zeroth law of thermodynamics looks like this. Okay, and it has something to do with thermal equilibrium. Okay, now if you notice, and this was and the statement for this one is also very, very easy. By the way, you have done thermodynamics in chemistry, right? I'm not misunderstanding. Please let me know in the chat. You have done thermodynamics in chemistry, yes? Please type it in, guys. Okay, thank you. Okay, cool. So everybody knows what zeroth law of thermodynamics is. If I have a body, if I have A, B, C, three bodies, A is in thermal equilibrium with B, B is in thermal equilibrium with C, okay? Then A will be in thermal equilibrium with respect to C. So it's like if A is in equilibrium with B and B is in equilibrium with C, then you can say ki A is also in equilibrium with C. So that's the zeroth law of thermodynamics. And to be honest, it's one of those easiest ones. It's more very, very basic. Okay. And a statement I think everyone can give. But in terms of application, can we essentially come up with a definition or an example, a real life example that could be used to understand the zeroth law of thermodynamics? 1 second, let me turn this black. I'll be sharing the notes, don't worry. Okay. So this is the statement for the zeroth law of thermodynamics. If two systems are each in thermal equilibrium with the third system, then the first two systems are in thermal equilibrium with each other. So if in terms of A, B, C, it is very easy to understand. If A is in thermal with B, B is in thermal equilibrium with C, then A and C are in thermal equilibrium. Now, one example for this is essentially the experiment where you try to essentially okay, so let me describe this particular experiment. Now, what this experiment is, key, you have a paper cup and you burn it. Okay, you burn it in the sense you put it on a Bunsen burner, and immediately it will catch fire because the ignition temperature of the cup is essentially around 180 200 degrees centigrade. So as soon as the fire comes up, it burns, completely burns, because the temperature of the cup can reach 200s, and then it can ignite and it can burn whole. But in the same paper cup, if you put water inside of it and then put it over the flame, okay, and actually I have a video for this. Uh, if people are interested, I'll show it to you guys. One second. Okay. Okay. So let me share my other screen. Honest. Okay. 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 The last part, that you making tea on the cup, is not something that I'll advise personally on a paper cup. Okay. But the basic question is, why doesn't the paper cup burn when you put water in it? Okay. Zeroth law can be used to explain this. Now, in this previous chapter, you have studied something called the latent heat of vaporization. Anyone wants to tell me what latent heat of vaporization is? Guys, I need you to participate. It becomes very boring if it's one-sided. Okay, so help me out here. Come on. Someone let me know what is latent heat of vaporization. I'm taking a class, man. I'll talk to you in a bit, 2 minutes. Huh? Guys, what is latent heat of vaporization? Okay, it's the okay. Okay. So whenever a body changes from one state to the other, right? One state to the other, the temperature sort of changes. Okay, the temperature, the temperature remains constant. Why is that? Because if you start heating water, the water will keep on going like 10, 20, 30, 40, 50, 60, 70, 80, 90, and then 100 pay, it stops. And what happens to the energy that I'm providing if it's not increasing the temperature? Well, all that energy is getting utilized to change the state of the body from liquid to gas. Okay, so that would mean that water, till it has completely evaporated, will not be more than 100 degree, and that is the reason why the cup does not burn. Zeroth law of thermodynamics is that water and the paper cup are in thermal equilibrium, right? So if the flame is trying to heat them, it's trying to heat them both, and because of the thermal equilibrium, the temperature of the paper cup and the water is stuck at 100 degrees, and the ignition temperature of paper is 200. Okay, it's 200. So that is why the cup does not burn. The cup does not burn because of the because of the zero law of thermodynamics, and the idea that the flame is going to uh, heat them together, and because of that fact, you'll not be able to burn the paper if water is also involved. Okay, but as soon as again all the water is evaporated, the cup will again fully evaporate, right? Now, second thing that I want you to know, apart after zeroth law of thermodynamics, is the first law of thermodynamics. Now, first law of thermodynamics is pretty much based on the conservation of energy. Okay, the first law of thermodynamics is based on conservation of energy. Okay, where you say key delta Q is equals to delta U plus W. Give me 2 minutes, I'll be back and we'll start discussing what delta Q, delta U, and W is. Give me 2 seconds, pause. Sorry, I had someone at the door. Let us continue. So, first law of thermodynamics says that delta Q is equals to delta U plus W. Now, understanding this is pretty simple, okay? Because you have already studied what Q is in the previous chapter. Q is the heat energy, right? And I have said this to you before that heat energy is not like something is stored inside a body. Heat energy is not essentially stored inside the body. What gets stored is internal energy. Heat energy is like the transfer of energy between the surrounding and the system, okay, in both ways. So your system can either gain energy or it can lose energy. One of the two will things will happen, right? uh Delta U is essentially the change in internal energy, okay, and we'll talk about each of them in detail on what exactly internal energy is. And the last one is essentially the work done. Okay. Now this is where little work done is like very different in physics because of the perspective. Now, folks in chemistry, they find out the work done because of the piston. So if you have a compression or expansion of gas, what they focus on is what is the work done by the piston during this process. For us, for physicists, work done by the gas is going to be important, right? So this is work done by the gas, and this is the change in internal energy, and this is the heat energy, the energy transferred between the system and the surrounding. Okay, so this is the basic idea. Now how do you interpret this? Okay, so if you have a system like this and you provide heat, then it can be that heat that you provided to the system can be utilized in two ways. Okay, the two ways of utilizing this energy is that either it can be used to change the internal energy of the system, or the energy can be utilized by gas in doing some work done. Okay, so I want you to repeat after me, like when by yourself, right? Saying that whatever heat you provide, whatever heat you provide to a system, that can be utilized to change the internal energy of the system, or it can be utilized by the gas to do some work done. Yeah, कौन है टीचर कौन है? हाँ ठीक है, उनको बाहर बिठा दो, मेरा दरवाजा बंद कर दो। ओके, ठीक है. So again, let me explain. If you provide heat energy, and remember, all of these units are what? These are like same dimensions, joules. All of them are joules. Okay, all of these are joules. Energy unit of energy. Okay, so you are saying that whatever heat energy you are providing to the system can be utilized in changing the internal energy, and it can be used by gas to do some work done. Okay, so in a way, am I not saying ki here energy is not getting destroyed, energy is only getting converted to one form or the other, right? So Q is heat energy, and it is getting converted into what? Internal energy and work done. So what is first law of thermodynamic at its most basic is just conservation of energy. This is nothing but conservation of energy. Okay. Now I'll be very, very thrilled if somebody knows the limitations of the first law of thermodynamics. I'll be very happy. Okay. Please let me know. Is there anyone who knows what is the limitation of the first law of thermodynamics? Okay. Type it in the chat. I'll let you know if it is correct. Okay. So first law of thermodynamics is based on conservation of energy, which is very, very correct. Right? And it says ki whatever heat you provide is used in change in internal energy and work done. Now that is all of that is good, right? But there is also some limitations into this first law of thermodynamics. I mean, it's true, but there are still limitations. Anybody knows about these limitations that I'm talking about? See, that whatever that limitation, mass energy equivalence, that is pretty much the limitation of all classical mechanics or classical physics, right? All of this is not like mass energy conversion if starts happening. That's not like a limitation, it's like out of scope of the subject. Like that is a different. So whenever you're going for, or whenever you are understanding the idea of quantum mechanics, you're talking about subatomic particles, so you're going into celestial bodies. The general mechanics, like Newtonian mechanics, fail. All the basic stuff fails. Now that is not because physics becomes untrue there. It's just that the physics that are used to govern those is slightly different, slightly unified. Okay, and there is mass energy equivalence. But apart from that, like not going out of the scope, remaining in the scope also, there is a limitation here. See, the limitation is the direction of the reaction. Now, you might have talked about this in your chemistry. That's why the second law of thermodynamics comes into picture. if I say, if I say now imagine this, okay? Uh, let's say there are, you know what a Newton's cradle is, right? I think everybody knows what a Newton's cradle is. It's like those balls that are hanging, okay, uh, from the, I don't know, from the ceiling, not the ceiling, like whatever the frame is made of, right? And you take one of the balls and start, oscillating it. It will come this side, hit this, and the other side will start going up, and then the whole oscillation keeps on happening. And this is known as Newton's cradle. I think I have showed a couple of simulations when I was teaching different types of collisions. So this can be approximated to elastic collisions, but actually they are not. So if you let them be, uh, it will oscillate to some time, but all that energy will eventually dissipate. Now, can someone tell me that initially I have provided some potential energy and some kinetic energy? Like potential energy is like hidden in the form of kinetic energy only, right? So in this whole process, I initially my system had some 100 joules of energy in form of potential energy. Okay, in terms of potential energy it had, or in terms of mgh, or I can also say in terms of kinetic energy it had. Okay, now after some times, all the balls will eventually come to rest. Like it will take some time, but eventually it will come to rest. Okay, what happened to this 100 joules of energy? Where did it go? Tell me, guys, what happened to this 100 joules of kinetic energy that I gave to this system, or potential energy, whatever you want to call it? Whatever energy you gave, where did it where did it go? Yes, guys, type it in the chat. Yes, heat energy. And don't you think sound energy is also one of the outputs here? So this kinetic energy that these balls had will convert into two things. It will convert into sound energy, and it will also convert into heat energy. Why heat energy? Because during the collisions, the balls will heat up. Okay. There's also air resistance, which is like friction because of air. Now, okay, with friction, there is always heat associated. So this 100 joules of energy converted into sound energy and heat energy. Now, this will be explained by the first law of thermodynamics as ki, okay, 100 joules means if this one is 60 joules, or let's say the sound energy is 30 joules, then heat energy will be what? 70 joules. First law of thermodynamics, since it is based on conservation of energy, it will work like this. Now, this is fine, okay? But when you're using first law of thermodynamics, you are blind to the uh, direction of reaction. What I mean by that is if you said something like this, 30 joules of sound energy plus 70 joules of heat energy is equals to 100 joules of kinetic energy, or the reverse, it doesn't make any difference to the first law of thermodynamics. You can write both ways. Okay. Now, practically that is not possible. What I mean by that is if you hope to recreate this kinetic energy, okay, I'll keep the balls like this, okay, and I'll start to play the guitar in front of it, okay, to provide this sound energy, okay. And I'm expecting that if I play the guitar, the balls will get some kinetic energy. No, that doesn't happen, bro. It's not the reverse. The reverse is not true, right? The kinetic energy will slowly convert into sound energy. What I mean by that is the tuck 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 sound when they collide, it creates sound energy, right? So 100 joules of kinetic energy will convert into sound energy and heat energy. But if you take a lighter and burn the balls and you're like, I'll play the song for it and it should gain the kinetic energy back, it doesn't happen like that. Sound energy plus heat energy won't convert back to kinetic energy. This is what I'm trying to say. That is the limitation of first law of thermodynamics. Although it is based on conservation of energy, it does not have the perspective of whether that reaction is possible or not. See, kinetic energy converting into sound plus heat is allowed, but sound plus heat cannot create kinetic energy. That directional preference of a reaction is not discussed in first law of thermodynamics. That is why we need the second law of thermodynamics, right? So that is all about the first law of thermodynamics. Let us go in more detail here and understand more things about this first law of thermodynamics. Okay. Now, if I dissect and talk about all the individual individual quantities in the first law of thermodynamics, the first one is heat. Okay, we had a particular chapter called heat transfer where we pretty much studied everything about heat. Okay, so here you can notice what I'm doing here. This is like the conduction of heat. Okay, heat ka unit is essentially joule. Rate of heat transfer is essentially joule per second. Okay, but what we are using in the first law of thermodynamics is not rate of heat transfer, it's just heat itself. Okay. So usually it is given by ms delta T or something like NC delta T, right? Depending on what kind of quantity you are using. If you're saying molar heat capacity, okay, molar heat capacity, then you're talking about C, which is essentially heat capacity or the amount of heat required to raise the temperature of a body, not a body, 1 mole of a body by 1 degree centigrade, right? Specific heat capacity will be like the amount of heat required by 1 kg of substance to raise the temperature by 1 degrees. Okay, so that is the definition of what specific heat capacity and molar heat capacity is, and those quantities are used to define the heat. Now, heat is not a state function, so it's going to be different for different processes. Now, I hope you know CP and CV. Now, if I write something like Q is equals to NCP delta T, you know that this means that the process that I'm talking about is what? This is a constant pressure, right? I can write Q is equal to NCP delta T only if I know that in that process, the gas was at constant pressure. Okay. If I say Q is equals to NCV delta T, this means this is what? This is, okay, I'll write this down. This is constant pressure, and this is what? This is constant volume. Okay. So I have, if I write Q is equals to NCV delta T, then I know that process has constant volume in it. Similarly, if I just write Q is equal to NC delta T for any random process, now there are other processes as well, apart from constant pressure, constant volume. So for them, I'll write just N into C, and C will be the heat capacity for that particular process. But anyway, by the way, the 4 standard processes that we will be discussing in this chapter are isobaric, which means constant pressure, isochoric, which means constant volume, and there is isothermal, which means same temperature, adiabatic, which means there's a special equation P V raised to power gamma, which has to be constant. Okay. And the fifth one is the polytropic process, which is like the 4 standard process. So we have created these 4 processes, but there are cases which may not follow these 4 standard processes. So the fifth process that will talk about any random expansion with some random equation will be known as the polytropic process. Uspe bhi we'll talk about a little bit about it. It's slightly out of syllabus, but still it will give you the complete picture of what thermodynamics is. So we'll even talk about this. So I hope heat is clear to you. I hope heat is clear to you. Heat is essentially the transfer of energy from one location to the other. Okay, heat transfer happens in 3 different methods, and all this stuff we have studied, right? And the formula for that is ms delta T, mc delta T, and it depends on the process. It depends on the process. Okay, so please, if you have to take away, these are the takeaways that you can pretty much understand from this. The second word in the first law of thermodynamics, if you look about in this equation, is delta U. Okay, and delta U means it means internal energy. It means internal energy. Okay, now what exactly is internal energy, guys? Okay, now you know ki if you have a gas, the gas molecules, when they are inside a container, they're not at rest, guys. They're not at rest. Even now you'll be thinking like this. Uh, so what if I have a room full of gas and I close the door? I don't let anything interact with that room, and I keep it for 1 year. will the particles slow down? Will the particle eventually come to rest? The answer is still no. And can someone tell me why? Uh, you can use the chat again. 1 minute, take 1 minute to think and tell me why. As in, my question is this: if you have a container full of gas and you keep it isolated, you make like, uh, theoretically speaking, you make a concrete box that cannot interact with the surrounding. Okay, it does not, does not allow heat to transfer, and nothing is allowed. It's just that there are some particles inside. Okay, gas particles. Okay, ideal gas particles, and you just keep them there for 2 years. Will the particles stop moving eventually? That's the question. Think and answer. No. Yeah, but why? Why is no the answer? Okay, let me explain. See, the temperature of a body, right? Let's say your body is at a temperature of, I don't know, 40. No, 40 is too much. That would be too hot. Uh, let's say your body is 37. Okay, 37 degrees centigrade. Where does it get that energy? Like, why is your body at 37 degrees centigrade and not, or 37 would mean that 310 kelvins? Why is it not at 0 kelvins? Well, the answer is that energy is coming from what? The kinetic energy of the molecules, right? So when you say you put a gas at normal temperature, let's say 300 Kelvin, by default, this 300 Kelvin is created by the kinetic energies of these gas molecules. Okay, so the gas molecules which are moving from here and there, this random motion is what is creating the absolute temperature, and that absolute temperature in turn is what is responsible for internal energy. I hope that makes sense. Okay. Now, I know the basic idea in classical mechanics is when a particle, has the kinetic energy, it sort of moves. But here the gas is, I mean, the center of mass of the gas is not moving anywhere. It's still at the same location. But you got to understand, I'm not talking about that translational kinetic energy, the kinetic energy which is responsible for the movement of particles. Here, by the virtue of the collisions amongst themselves, the particles will keep moving from one place to another, and that is what is creating the absolute value of temperature. So yeah, I'm not even talking about delta U, I'm talking about U is internal energy, and it is actually given by ncvt, right? So at a certain temperature, guys, uh, the internal energy of the system will be given by number of moles into cv into t. Okay, ncv into t. Now, people get confused. Ki, sir, why did you use CV here? Isn't this like a state function and not dependent on the path? Why are you using constant volume? And what if I am doing like a adiabatic process? वहां पे तो volume constant नहीं रहता है. In an adiabatic process, volume is not constant. Then how can you say that the universal formula for internal energy is NCVT? How do you know that? Okay. Well, I know it because of the fact that it is a state function. See, if I do different processes and I want to find out what is internal energy, I can find out internal energy very easily in a isochoric process. Now, let me remind you what isochoric processes are. Isochoric process means that the volume is equals to constant, right? It is not changing the volume, right? If volume is not changing, bacho, then can you tell me what is work done? Well, work done will be zero, because as you have studied before, work done is force into displacement. In case of gases, it is pressure into change in volume. But if the volume is not changing, right? If the volume is not changing, then work done has to be zero. Now, if you use the first law of thermodynamics, It says ki Q is equals to U plus W. And for a isochoric process, work done becomes equals to 0. So this would mean that U will become equals to Q, right? But Q ka value is to NCV delta T. For a isochoric process, Q ka value is NCV delta T. So from there, I understood that U will be equals to NCV delta T. Now, although I have done it for isochoric process, won't this internal energy true for any other process as well? That means if I take a isochoric process, then also it will be NCV delta T. If I take adiabatic process also, then also U will be equals to NCV delta T. This is the beauty of a state function. In a state function, if you are able to find its value through one of the processes, that same value will be valid for any other process as well. And the reason for that is that it does not depend on the process. So you take up a process where finding out that value becomes really easy, and then you just copy paste it to every other process. And that is why we say that internal energy is equals to NC. That change in internal energy is equals to NCV delta T. This is why we say that. And it is across the board, guys. It is across the board. It is a state function. So that is why NCV delta T will be true for, any process. For any process across the board, delta U will be NCV delta T. Okay. Now you gotta understand, if this is not an indication of the process, please do not try to interpret the process by looking at the coefficient of delta U, because I'll write this equation, and if I hadn't explained all of this, this would have blown your mind, and you'll be like, so what on earth you are doing, right? Now notice this. I'm going to derive something called the Mayer's relationship. Mayer's relationship. Okay. Now, what is Mayer's relationship? Let us understand. I'll write in a isobaric process. Isobaric process. Again, let me remind you what isobaric process means is that P is equals to constant. Your pressure does not change. Okay. Now, in a isobaric process, I'll say ki Q is equals to U plus W. Whatever heat you provide can be utilized to change the internal energy, or can be utilized by gas to create some work done. That is the statement I have written. Now Q ka value will be NCP delta T. Because Q is not a state function, the specific heat capacity will actually be like process dependent, right? You'll be saying ki, NCP, because pressure is constant. CP is what? Heat capacity at constant pressure into delta T, right? What is delta? What is U? U will be NCV delta T, okay? Because it's a state function, it doesn't depend on the process. Its formula is always NCV delta T. Plus work done for, I'll teach you how to find out work done, but for now, just assume it is P into delta V, okay? Which from ideal gas law can be written as P into PV is equals to how much in ideal gas law? PV is equals to nRT, right? So P delta V will be equals to what? nR delta T, right? So that is what I'm going to use in the next line. NCP delta T is equals to NCV delta T plus nR delta T. Now, before going ahead, I just want you to notice this. NCP delta T is equals to NCV delta T plus P delta V. This equation itself, if you're not paying attention, you will completely get flabbergasted with this equation, because it has CP and CV in the same equation. Now, for someone who is not accustomed to the fact of what is going on here, they will be like, sir, you have a number that says constant pressure. Okay. You have CV, that means constant volume. What are you trying to imply? Which is going on? Is it constant pressure or constant volume? Okay, the answer is very, very simple. The first coefficient here, Cp, is coming from heat, which is a process dependent force. The Cv right here has nothing to do with what process is going on. If I had written an adiabatic process also, this would have been Cv only, right? So this CV right here is not the determining factor of what process is going on here. This one is, right? Although N, Q and U formulas look very, very simple, do not get swayed by the similarity. Here, Q pay, whatever heat capacity you put, that will be going to determine what kind of process you're using, right? If you have a constant pressure wala scenario, then you'll be using NCP delta T. Constant volume pay, you'll be writing NCV delta T, and so on, right? Adiabatically, you'll probably write, there is no special symbol. You can write ADI at the bottom, and it will be the heat, molar heat capacity at adiabatic process. I think heat to in the adiabatic process is zero only. I don't think you'll need the heat capacity for it. Isothermal ke liye also, I think delta U will be zero there. So whatever heat you provide, it will be work done. But anyway, all of that we'll discuss in a bit. But at the end of the day, basically what you have to understand is that Q is process dependent, U is not, right? Now, if I simplify this equation, I think n delta t will cancel in all the terms, and you get that famous equation. I think everybody remembers this one. Cp is equals to Cv plus R. This is known as the Mayer's relationship, one of the most beautiful equations in thermodynamics, where you relate the molar heat at constant pressure and molar heat at constant volume, right? But again, the derivation makes no sense at the second line if you're not comfortable with the fact on what exactly is heat and what exactly is internal energy, right? So I hope this made sense, guys. Please let me know if you have any doubts. I'm willing to take doubts at this point. Please let me know if you have any doubts. Okay. So basically, the gist of internal energy is that internal energy is a state function. It is dependent on temperature. Uh, temperature is essentially something that defines the internal energy. At a certain temperature, the molecules will have both potential energy and kinetic energy. Okay, and this potential energy and kinetic energy, if you add them, that is known as the internal energy, as you can see from the diagram here. Okay, if your gas has a certain temperature, that means because of the virtue of the temperature, the particles will have their own potential energy and kinetic energy, because kinetic energy and potential energy of the molecules is what is creating the absolute temperature, 500 Kelvin, 200 Kelvin, whatever temperature it is at. So hypothetically, at 0 Kelvin, you'll have like zero energy, zero internal energy. Okay, so that is the basic idea there. Okay, so if you have any doubt, again, feel free to ask. uh, I think I want to quickly talk about the internal energy graph. Okay. Uh, I like to make this graph as well. If you have a PV graph, you can show like this. If your body is coming from, let's say, some point A right here. Let's use a color like point A right here. A body is coming from A to B in three different processes, right? But the initial volume is V1, initial pressure is P1, final volume is V2, final pressure is P2 for all three processes. So regardless of how much work was done or how much heat exchange was happening in all of these three scenarios might be different. They might be, not might be, they will be different, because work done is area under the curve, but I will discuss later. But what I'm trying to imply here is that 1, 2, and 3 pay, you'll have heat different, you'll have work done different in all three processes. But delta U, since it depends on the final value minus the initial value, it doesn't matter. Okay, be it 1, be it 2, or be it 3, delta U will be same across all the paths. It will be same across all the paths. Okay, and the value, the change in internal energy, bacho, is directly how can I say this, is directly proportional, or it's directly proportional to delta T. Okay, it's directly proportional to delta T. That's what you have to remember. Please let me know if you have any doubts. No? Okay then. Last part of my discussion is going to be on work. I mean, last part of the discussion on first law of thermodynamics, my focus will be on work, right? Now, I think all of you remember what work is. Okay. So the most basic concept of work is like if you have force and you're applying a force and that is able to create some kind of displacement, right? Then work done was, I think you remember the most basic formula for work done is saying that work done is force multiplied by displacement. So in this case, you see there is a 12 Newton force that the person is applying and he's creating like 5 meter worth of displacement. So the work done will be like 12 into 5 and you're going something like 60 joules. And if you want to find out what power is, you'll do work done by time. So it's like 60 joules divided by how many seconds? Look here, it says 3 seconds, right? So it becomes like what? 20 watts, 20 watts. Okay, so all of this you have done in a few chapters ago, right? But how do you find out the work done in case of gas? Also, before going into that, this is a very simple formula, but this year we studied that work done have to be interpreted in a vector form like force dot displacement. So we advanced the formula. This is like pretty much from 9 standard. I think everybody knows this. 11 standard may we value the value we added here is the vector format for this, where we understood that it is not just Fs, it is Fs cos theta. So that means if you have a force in a certain direction and displacement is happening in the opposite direction, then there's a possibility the work done will come out to be negative, right? Because of this cos theta, right? And there is also this possibility that there is both force and displacement, but the work done is zero because the angle between them is 90 degrees. That also we have studied in the previous chapters, right? That force into displacement can be negative also, or the work done can be negative also if the force and displacement are in opposite direction, right? There's also this idea that what if you have a force which is dependent on displacement itself. What happens if you have a force that is dependent on displacement itself, as in force is equals to kx? How do you find out the work done in this case? Well, if you remember, if force is a function of x itself, then work done used to be found as integration of force with respect to displacement. I hope you remember this. Okay, I hope you remember this. Integration of force with respect to displacement if your force is like a function of x. Okay, now I'm going to use this in terms of gas. Now imagine that I have a compartment full of gas. Okay, so pardon my drawing here. I'll try to draw it with a tool here. Let's see if we can do this. Okay, let's try to make one. Let me fill. No, I don't want no fill. This one, I need like a smaller piston, like variation for this. Guys, wait a second. I'm trying to make this beautiful. Let's see if I can do so. Damn it. I can't. Okay. So let's say there is a container. Okay. And the container has gas inside of it. Okay. And let's say I'm concentrating only on the right wall. Okay. On the right wall. Now, from the point of perspective of the gas, okay, and because I want you to understand the chemistry perspective as well, uh, I would like to make the piston like your chemistry teacher would have made. Okay, this is the container that has the gas, and what the chemistry folks make is also the piston, which is responsible for keeping this gas inside. So this is my piston. I think your pistons will also have like a small handle to push it. So this is the piston. Okay. The container ends here. Okay, so I hope this is clear to you what I'm trying to make here. So it's like a syringe thing. Okay, the piston is pushing the gas inside. Now, guys, I need you to understand this. Okay, from the perspective of gas, gas is applying pressure. What? Where? Like what is the force because of the pressure? Well, it's always outwards. You'll never see the gas is pulling the piston in. It doesn't happen. Any kind of wall, any kind of scenario. If you inflate a balloon also, the force that the gas is applying is on the outside, like it is trying to push it outwards, right? This is where the force is always acting for the gas. Okay, and it makes sense to find out the work done of gas, right? So I know that the force is acting in this direction. Okay, force by the gas is acting in this direction, right? Now, how will you find out work done? Well, you'll say ki work done is equals to force into displacement. This is what we have studied, integration of force into displacement. But finding out the force because of gas molecules is like a humongous task. How much, how will you find out? See, there is a way to find out, and we will study that next chapter, which is known as the kinetic theory of gas, which is by finding out what is the change in momentum and then dividing it by time, basically using the second law to figure that out, right? Now, however, what we are going to do here is I'm going to divide and multiply this equation with area. Okay, so I'll do F by A and then area into dx. Okay, what am I going to do next? Someone in my class said ki I'll just cancel out A and A. Then why did I multiply, dude? Why did I multiply if I'm just gonna cancel this out? That's not the next step, Bachu. That's not the next step. Definitely not the next step. Right? Next step is I'm going to take F by A as what? Pressure. Because force by area is what? Pressure. Now think about what this is. Area is meter square and displacement, small displacement is m. So multiply these, this becomes meter cube. So what is this? What is area into small displacement? It is the small volume. This is how you get the formula for work done. You say work done is integration of pressure with respect to volume. But where did you get that formula from? From the same basic rule of work done which we have been doing for classical mechanics for a while now. Force into displacement, right? So work done is what? Integration of pressure with respect to volume. Now my question to you is this. If the gas is expanding, that means force is acting outward and the piston is also going out, what will be the sign of work done? Well, it will be positive. Okay, because when expansion is happening, the walls will move outward. When you expand the balloon, it becomes bigger like this, and you have force like acting in this direction. So what is the direction of displacement? Well, direction of displacement is outward. This is displacement. This is displacement. This is the direction of displacement. What is the direction of force? The direction of force is also outwards. So it makes sense that work done would be positive during expansion. And again, remember, we're talking about work done by the gas. Hence, I'm taking the force by the gas. Gas is always outwards, right? What about compression? When compression is happening, what happens? Well, when the compression is happening, that means this piston will be moving inside, right? Now, what happens if the piston moves inside? Gas, though, it's always applying force outwards only. So displacement is now opposite to the direction of force. So that is when the work done becomes negative. That is when it becomes negative, bachalo. Okay, so guys, understand this is what is the takeaway from all of this. I'm going to write the summary for this. If you have, okay, if you have compression, if you have compression, your work done will be negative, and that is because force and displacement are in opposite directions, right? Work done by the gas, by the way. Again, in physics, always remember we're finding out work done by the gas, not the piston. Piston is of no importance to us. Okay, it's the gas that we are working with. Chemistry people is because I don't know for some reason piston is very important. Gas is not important for them. Piston is important. So they're finding work done by piston. But we are same. Okay. Physics people are same. We are finding out work done by the gas because that is what we are studying. The idea of the kinetic theory of gas, thermodynamics of the gas, not the piston. Who is studying thermodynamics for the piston? I don't know. Chemistry people are studying thermodynamics for piston. So anyway, back to our discussion. This is something that I need you to remember. It's completely different in and the convention is like completely different in chemistry. So you have to adjust because unlike me, you cannot diss chemistry. It's also like part of your subject. So you have to be, defending both the subjects, which are telling different things to you, right? But again, you gotta understand ki if a physics person solves a thermodynamic problem and a chemistry person solves a thermodynamic problem, they're gonna end up with the same result. One is going to say ki work done is negative, one is going to say work done is positive. But end of the day, they are saying the same thing now. It is going for if the physics person gets like positive, uh, he will say expansion is happening, and chemistry person gets work done as negative, and he says expansion is happening. So at the end of the day, the result is that the gas is expanding. Whether you define it with a positive sign or negative sign does not make sense, does not make any difference, to be honest. Okay, so both of them perspectives are correct. It's just that physics one makes more sense. Okay, anyway, so work done is negative for a compression. Work done is positive for a expansion. Okay, so this is something that I need you to remember. Okay, but at the end of the day, the formula for this is very, very simple. Formula for the work done is what integration of P dot V. Okay, so this is the basic idea here. So please note. So as you're heating, the temperature also increases. And what I wanted to show you is this formula right here. Please remember this formula. Work done is integration of P dot dV. Integration of P dot dV. Okay, so if your gas is expanding, then you know your turn is going to be positive. If you're cooling it down or something, and then your volume decreases, then work done will be negative, right? Will be negative. But that is the qualitative analysis. We also need to figure out what is the different values of work done in different processes. And we'll start with the most easy one, uh, finding out the work done. Let me ask you, and you use the chat to answer me. What is the work done in a isochoric process? Okay, let me introduce you to all these processes. I don't think I have to spend too much time in these processes because you have already studied what this means. Isochoric just means volume is constant. Volume is constant. Okay. And what is work done? Work done, bacho, is integration of PdV, right? Which clearly states that you have to multiply pressure with what? Change in volume. Dada, if you have a process that itself defines that volume is constant, then work done will always be zero. Please note that down. For work done in an isochoric process is always zero. And how do you show the graphs for these ones? Okay, how do you show the graphs for an isochoric process? Well, this is how. This is how. Let me paste this. Okay, if the volume is constant, this is how the graphs will look. Okay, notice how these are vertical lines. In a PV graph, if you have to show that the volume is constant, you make a vertical line. And one more thing I need you to understand about the work done is that whenever you are making like a PV graph, the area under the area under the curve is going to represent what? It's going to represent the work done. It's going to represent the work done. Okay. Now, under a vertical line, if you have a graph that has a vertical line, what is the area under the vertical line? Well, there is no area under the vertical line. So hence, the work done will be zero. The work done will be zero. Please let me know if you understand this. If you have any difficulty, again, feel free to ask. Feel free to ask. Okay. Back to our discussion. I hope everybody has noted this. Work done in a isochoric process. Very easy, guys. This one is like the easiest one. Work done will always be zero in a isochoric process. Okay. What about something like this? Uh, Isobaric process. Isobaric process is what? Well, isobaric means pressure is not changing because bar is like unit for pressure, BAR. Okay. So isobaric just means constant pressure. Pressure is constant. Okay. Now, again, this is also like the second best one. Again, it does not require a lot of effort because work done will be something like integration of PdV. Okay. Which will be like now all of you have done enough integration to understand that if pressure is constant in this integration, you can take it out of the integration symbol and then you can simply write integration of PdV. Now this I cannot do. I cannot do this if pressure is not constant though. But this process tells me it is constant. That's why I'm taking it out of the integration. And I can write V initial and V final as the limits. And when you do integrate, you're just going to end up writing something like V final minus V initial like this, right? So which is nothing but P delta V, right? So work done in case of isobaric process is pressure into change in volume. Okay, where pressure is constant and you just have to figure out what is the change in volume. V final minus V initial. But I can also use the ideal gas law to say this is also equals to nR delta T because we know that PV equals to nRT, right? So that means P into delta V can also be written as nR delta T. But remember, this is only for isobaric process. Okay. So in isobaric process, how do you find out the work done? You find out by saying it is equals to P into delta V. How does a graph look like for isobaric process? Well, this is how it looks. Isobaric means horizontal lines. Horizontal lines, right? You could have it like this, A, B, and the process is happening like this. You can also have an isobaric process like this, where the process is happening from A to B in the reverse direction. I need you to just tell me which of them work done will be positive. Well, the first one, okay, okay. I know it's positive work done because if you look below, you will notice that when the body is going from A to B, the volume is increasing, okay. I can notice from here that when the body goes from A to B, volume increases. That's why work done is positive, right? And in this graph, although it looks pretty much identical to the previous one, but here you can see that volume is decreasing, meaning work done will be negative. Okay. So we'll meet again in 20 minutes. Okay. 11:15. Till then, have some breakfast and I'll see you on the other side. Again, if you have any doubts, feel free to type it in the chat. I'll clear it. Welcome back, students. Let us continue our discussion. Guys, we have studied how to find out work done in a isochoric process. And we have also found out how to find out work done in a isobaric process, which formula for which are like really easy. For example, work done in a isochoric process is 0. For a isobaric process is just nr delta t or p delta v, right? Let's do a little bit more complicated ones. The two other ones are like slightly complicated. The first one is how do you find out work done in case of a isothermal process? How do you find out the work done in an isothermal process? Okay. Now, isothermal process means that temperature will not change. Okay. Now, the process work done ka definition, it does not change. It's always pressure into change in volume. But this time I can't take out pressure outside because pressure is not constant in an isothermal process. Temperature is. So what should I do, guys? What should I do? If I can't take pressure outside and I also cannot, integrate pressure with respect to volume. So I have to write pressure in terms of volume somehow. Now I'm going to use the idea of ideal gas law, which says PV equals to nRT, right? So from here, I know that pressure is equals to nRT by volume, right? So I have expressed pressure as a function of volume, right? And that is how I'm doing what? That's how I'm finding out work done. And I'm going to write, in place of pressure, I'm going to write nRT by volume into dV, right? Now I can take some quantities out of the integration, nRT. These three things I can take out of the integration, and my integration just becomes dV by V. Notice that how I took T outside the integration because I know temperature is a constant, and any constant in integration can come out of the integration, right? Volume obviously can't come out because we are integrating with respect to volume. And let's say I put initial volume to find a volume limits also I put. Right? Now, if you remember, integration of 1 by x dx is given by log of x or ln x, ln of x. Ln x is nothing but log x to the base e, right? When you put a base e, you can also write it as ln x, right? So that means this equation can be written as nRT ln v final by v initial. How do it become V final by V initial? I'm also using the formula log of A minus log of B is equals to what? Log of A by B. So you know the integration is ln V, right? But when you put the limits ln Vf minus ln Vi, right? It becomes ln Vf by ln Vi. Okay. And yeah, this is the work done, guys. But sometimes what happens is sometimes you'll not have the data on volumes, you'll have it on pressure, right? What if instead of initial volume and initial volume and final volume, they give you initial pressure and final pressure? How do you work with that? Well, in an isothermal process, Boyle's law will be activated. Boyle's law, if you remember, is P1 V1 is equals to P2 V2, right? So this would mean V1 by V2 is what? P2 by P1. So this equation can also be written as nRT ln P final by P initial. This is something that you have to remember, right? The work done formula for constant or constant temperature, or I would say something like isothermal process, the work done in an isothermal process is given by nRT ln V final by V initial. Okay, so I think I made a mistake here. It's not P final by P initial. It's inversely proportional. So it will be like P initial by P final. Okay, so this becomes nRT ln Vf by V initial, or nRT, ln, P initial by P final. Any of these formulas you remember and you should be okay. This is how you find out the work done is in a isothermal setup. Please let me know if you do not understand any particular part of this. Uh, okay. Uh, Please let me know if there is any doubt regarding this. Okay. Any doubt, guys? Any doubt on this? No? Okay. Now, last one, guys. Last one. By the way, do you know how isothermal graphs look like? Okay. Uh, Isothermal means pressure into volume is supposed to remain constant, right? Now, I don't know how much you have completed in your maths, but if you have a graph and you put V in the x-axis, pressure in the y-axis. Now, this is an equation that looks like x into y is constant, right? And it's a very pleasing looking equation. And in math, this equation represents something called the rectangular hyperbola. Rectangular hyperbola. Now, if you are aware of this particular website, desmos.com, okay, your math teacher might have definitely talked about this because I know him. He loves desmos.com. Anyway, so what desmos.com does is if you put like an equation into that, it will always give you what kind of graph it will look like. So you can put x into y is equals to 5 or any kind of constant or 10 or whatever number you want, and it will tell you that the graph for this will look like this. Okay, so this kind of a graph is known as rectangular hyperbola. X and y axis will act as asymptotes. Now, I hope you know what this word asymptote means. Asymptote. Asymptote is essentially like the two graphs, the two curves that we are talking about will always, it will always come closer and closer to one another, but they will never meet. Okay. You know what? I'll show it to you. I'll show it to you. Okay. Because I have access to internet. Let us just do it. Okay. Let's desmos.com. I'm opening desmos.com. Let me share my screen with you guys. Okay. So this is how the Desmos website looks like. Okay. Desmos.com. Go to graphing calculator and you write the equation. Okay. Here you just write x into y is equals to some constant and you put a slider for c equals to 1. So here you can notice, by the way, the graph will also be in the third quadrant as well, where we don't want to talk about the third quadrant because it's this one is math. Here x and y both can be negative also. That's also one possibility, but for us we are doing like practical application, so we'll notice that pressure and volume, they will never be negative. Okay. What do negative volume even mean? So here, this is what I was talking about. This is known as a rectangular hyperbola, the red curve right here. Okay. And here you can notice how if I take this to the right, you will notice that the two lines, the x-axis, which is like the black line here, and the red line are always coming closer to one another. But if you zoom in, there's always this distance between them. They never meet, right? So they're always coming closer to one another as you go forward and forward and forward and forward. They're always coming closer. There's always this gap which keeps on increasing, decreasing. The gap between the two lines always keep on decreasing, but they will never meet. They will never meet. They will never meet. In reality, they will never meet. Okay, so you can see that the distance is increasing, and then you have this graph. And as you increase the distance, or P into V, if you increase the distance, you'll notice that the graph moves further away, but the sort of behavior or the nature of the curve does not change. It's always coming closer to the x-axis, always coming closer to the y-axis. So that is like a representation of what this is. Okay, so these are known as isotherms as well. These graphs are known as isotherms. Okay, this is known as the isotherm. Okay, so I hope everybody is clear on this. Okay, and in the graphical format, this becomes a little bit difficult to find out because there is no formula to figure out what is the work done, right? Yeah, from the graph. So you here also, if you want to find out what is the work done, you'll always have to revert back to this particular formula, which is like nRT ln v final by v initial. If you know this, then only you'll be able to find out the work done, not from the graph directly. Because if you have like horizontal graphs and all, you have formulas for this. Length into width. If it's a rectangle, is length into width. But yeah, for something like this, it becomes a little bit difficult. Okay, but anyway, let us continue. Let us continue and discuss the last standard process. Okay, the last standard process that I want to be talking about is the adiabatic process. Adiabatic process. Now, this is, I think, the most confusing for students among all the four standard processes. Adiabatic process is essentially the one uh, that that confuses students. Okay, now there is this idea that Cp by Cv. Cp, now what is Cp? This is the molecular heat of a gas at constant pressure. And Cv is like molecular heat capacity at constant volume. If you divide the two numbers, you always get this constant, which is known as the adiabatic constant. This is gamma, and gamma is known as adiabatic constant. So this is a special number. Okay, and this special number, why do I say it's a special number? Because it is fixed for a gas. So if you know, if you know that it is a monoatomic gas, it is a monoatomic gas. Okay, then you know this gamma is essentially equals to I think it is 5/3. Okay, and if you know it's a diatomic gas, now what is monoatomic gas? Monoatomic gas means something like helium. Okay, like in one molecule of helium is both an atom as well as a molecule, because helium do not form like multiple atoms, do not come together. It's a monoatomic gas, right? Helium, every noble gas is like a monoatomic gas. Think about diatomic gases, something like O2, N2. These are what diatomic gases, right? There are two atoms in a molecule. Then for this, the gamma will be fixed again, and that is equals to 7/5. And the rationale behind why these numbers are coming the way this is, uh, I'll make you understand next chapter when we talk about specifically about gases, these kind of gases, on why exactly this is 7/5, something to do with the degrees of freedom and everything, right? And if you have polyatomic gases, non-planar polyatomic gases, I'll just write polyatomic. We'll go about the details of it when you study kinetic theory of gas, something like NH3. Okay, do not give the example of CO2. CO2 is not going to have the same gamma as polyatomic gas. It is actually an exception, and we'll talk about it next chapter. But NH3 is one valid example. For this, this is going to be 4/3. It's going to be 4/3. So these are the special numbers for these gases. Okay. Now, adiabatic process suggests that the exchange in heat during this process will always be zero. It will always be zero. So that means in the first law of thermodynamics, which says that Q is equals to U plus W, Q is equals to U plus W, I'm saying that this term right here in an adiabatic process will always be zero. There is no heat transfer. There is no heat exchange between the system and the surrounding, right? So finding out work done is actually easy in this one, because work done then will be equals to minus of U. And all of us know the formula for U. Regardless of what process it is, tell me what is the formula for U? It is NCV delta T. Again, people get confused because again you're using molar heat capacity at constant volume, but you're saying it is a adiabatic process. Does it mean volume remain constant in an adiabatic process? Nah. CV is not an indication of what process this is. This process may be an adiabatic process, but still we are using that number CV. It doesn't mean it's a constant volume molar process. Okay, just because I'm using CV doesn't mean it's a constant volume molar process. It's just because of this sheer, this idea of internal energy being a state function that everywhere U goes, CV comes with it, right? So that's why work done is minus NCV into delta T for a adiabatic process. Okay. So why did you teach us all of this stuff? This is not even required to find out work done. Well, it is required for something else. I'll tell you what. Okay. Everybody has written this. I've shared a note, don't worry. Okay, so work done is minus NCV delta T in case of a adiabatic process. Now, what I was telling you is for every process, there can be a standard equation that can be written. Like, for example, isobaric you'll write pressure equals to constant. Isochorically, you'll write volume is equal to constant. For an isothermal, you'll write pressure into volume is a constant. Okay, what do you write for an adiabatic process? So, adiabatic equation is actually, this will look like this. PV raised to power gamma is equals to constant. Now, I'll tell you what major mistakes or what major misconceptions people have is they think that this number could be anything. But the answer is no. Okay. We have to understand that you could have a process something like PV square equals to constant, but I won't call it adiabatic because this gamma value cannot be 2. There are only 3 possibilities here. 5 by 3 for a monoatomic gas, 7 by 5 for a diatomic gas, and 4 by 3 for a polyatomic gas. So if I know that this gamma, this number that you have put in the power is essentially, one of those number, depending on what gas you have, then you call it adiabatic process, right? So if you see PV raised to power 2 and equals to constant, you can't say, this is an adiabatic process because 2 is not the gamma for any of these processes, right? Now you got to understand that PV raised to power gamma is equals to constant. If I use PV equals to nRT to write this one, then I can also write P as nRT by V, right? So which means this equation, this original equation that I wrote here can also be written as something like nRT by V into V raised to power gamma is equals to constant. Now, what I'm going to do is I'm going to take N and R to the other side, which are like constants. And also constant divided by constant will still be a constant. This is how the equation would look. T into V raised to power gamma minus 1. How did I get gamma minus 1? It's like V raised to power gamma divided by V is V raised to power gamma minus 1 is going to be a constant. Okay, so this is alternate way of writing the adiabatic equation. So if you get something like temperature into V raised to power gamma minus 1 is a constant, then also you can say that process is adiabatic. That process is adiabatic. Okay. So an equation that looks like this will represent adiabatic process. I hope everybody is clear on this. Please let me know if you have any doubts in this. Okay. You have any qualms about this equation? Okay. And I hope everybody is clear on this. Okay. Now, gamma, this is another thing that I need you to derive. Okay. Gamma can be written as, one second. Gamma, sorry, not gamma. CV can be written as gamma divided by, R divided by gamma minus 1. And CP can be written as gamma into R divided by gamma minus 1. Derive. I'm going to give you 2 minutes to try. Please, can you derive these two equations? It's a very easy equation to derive, but I will ask you to derive. Just try 2 minutes. If you can't, then I'll also give you hints. Come on, guys. Let me know how I'll use this. Okay, no doubts. So let us continue. Uh, I'll help you derive this. Okay. So first equation I'm going to use is Cp is equals to Cv plus R. Now this is known as the Mayer's relationship. We derived it a bit ago. Few seconds ago, I think we derived this. It's an important relationship in uh, in in uh, in thermodynamics. Okay, the second equation I need you to understand is that Cp by Cv was just defined as gamma. So from the second equation, Cp can be written as gamma times Cv. And this particular result, if I put in the first equation, it is the second equation is your result nikla hai. I'm going to plug it in the first equation. So I'll get something like gamma times Cv is equals to Cv plus R, right? What can I do next? I can take Cv to the other side. Cv gamma minus 1 can be written as R. So that means Cv can be written as R divided by gamma minus 1. Okay, so if we know the value of gamma, Cv value can also be like found out really, really easily. Uh, and gamma values you're supposed to remember. For monoatomic, diatomic, and polyatomic gases, please remember the values, right? And Cp is simply what? Cp is gamma times Cv. Now we have found out the value of Cp, so just multiply gamma with the value that you found out, and you get the second equation. So this is another way, or this is one another relationship that I need you to remember uh, for use in solving questions. Okay. And yeah, this is how you do it. Again, if you have any doubts, feel free to ask. Okay. Now, people get stuck a lot in graph questions. So I just wanted you to understand a few things about the graphs. Okay. Now, you got to understand that the adiabatic process that I have written, PV raised to power gamma, is also going to be looking like this. Okay. It is also going to looking like this. Very, okay, what was that? So beautiful, so elegant, just looking like wow. So yes, this is how the graph will look, just like wow. So so this will also look like an adiabatic curve. Now this poses a threat to me. I just understood that isothermal graph will also look like this, and this kind of graph will also look like this. So if I have an equation that says like PV equals to constant, and you also have PV raised to power gamma is equals to constant, how do I know which graph will go above, which graph will go beyond? Or below. So in that case, what I'm going to use, Pacho, is again the same tool. Okay. I'm going to use the Desmos, the desmos.com website that I was talking about. Okay. So let me share my screen with you guys. I've already plotted the graphs. Okay. So I need you to understand which graph. I just don't want you to memorize which graph goes up and which graph comes down. I need you to also understand it. Okay. So I hope you can see my new screen. I'm sharing my adiabatic versus isothermal wala graph that I have plotted. So here you can see the first equation says x into y raised to power, x into y is just constant. So the red graph here represents what? The adiabatic or the isothermal. This is P into V is equals to constant. So that means this is the red graph is the isothermal graph, right? Now the second graph is y into x raised to power z is equals to constant. So it's like saying ki, you have a adiabatic process because you're raising it to power something. So this 2.1 is actually not correct. It should be something like what is for monoatomic gas? It is uh, 5 by 3. So I will plug in the value of 5 by 3. So 5 by 3. Okay, so this is how it will actually look like. Okay. So, so PV raised to power gamma is equal to constant is given by this green graph, right? Now, I need you to understand this part right here. Okay, this part right here, the red one is above the green one. Take a second to think on why this adiabatic graph is below the isothermal graph. Why is this happening? Why is this such that the isothermal is above and adiabatic is below? Okay, so think about it. I'll give you the answer. Okay, just let me change my screen. Okay, so the topic for this one is isothermal versus adiabatic graphs. Okay, and I'll take a screenshot. I'll take a screenshot of what we just witnessed, and then I'm going to mark the diagrams. Okay, I'm hoping I'm sharing the correct screen. Yeah, I am. Okay, so the red one represents isothermal, and the green one represents adiabatic. Okay, so and by the way, what is there in the x-axis and y-axis? This one is pressure, this one is volume. So this is a pressure versus volume curve. Okay, this is a pressure versus volume curve, the isothermal versus adiabatic graphs. Okay, now and the explanation, I hope you have thought about this. Now see, if you say keep P into V is equals to constant, okay, so if you increase the volume, so in the graph, if you notice, if you increase the volume, so that means if you're going towards the right, the value of pressure is supposed to drop, like, because if you're saying okay, pressure into volume has to remain same, then if you increase the volume, pressure has to decrease to remain, to make it to make it a constant, to make it a constant. Okay, then PV raised to power 5 by 3 also works like that. Okay, so if you increase the volume, uh, the pressure will also go down, right? Now, what happens is that in case of a isothermal process, if you double the volume, pressure will become half, so that 2 cancels. Because when you are doubling the volume, uh, this thing will just double up. So the pressure will immediately fall by the same factor, but in the reverse direction. So if you double the volume, pressure will become half. If you make the volume 3 times, pressure will become 1/3 the value, right? So there's like proper inverse relationship is there. But here what happens, now this is 5 by 3 is something greater than 1. So it's like 1.33 something, right? 1.33. When you double the volume in this case, because it is raised to a power of a number which is greater than 1, volume gets doubled, but the effective increase in volume will be more. When I say that, don't understand it physically, I'm talking about the math behind it. So if you replace it with 2 times of V, then pressure will not be 1 by 2, it will be more. The reason for that is because when you do 2 raised to power 1.33, this will actually be closer to 3. When you're doubling the volume, pressure will become 1/3 to cancel these values out. I hope that makes sense, right? So this would mean that in an adiabatic curve, as you increase the volume, because of that power, which is greater than 1, pressure will fall faster. Pressure will fall faster. And that is why in this graph, as the volume goes ahead, the pressure falls much faster in case of the adiabatic scenario. And that is why if you have an isothermal graph and an adiabatic graph, the adiabatic graph will always be below the isothermal curve. Okay, so that is the basic understanding of what isothermal and adiabatic graphs would look like. Few other things that I need you to understand about the different graph systems is like, okay, for example, one thing I need you to understand is this is how all the graphs, if I put together, like all the different processes, this is how the graphs will look like. Okay, so the graphs of all the standard processes, I need you to draw them. Okay, all the standard processes will like combinedly look like this. So isobaric is a horizontal line, isochoric is a vertical line, isothermal is that perfect rectangular hyperbola. Adiabatic also looks like this, but it is below the isothermal. It's not like symmetric about the x and y axis. Adiabatic is going to be slightly, how can I say this? It's slightly below the isothermal. It's not perfectly symmetrical to the x equals to y axis. Okay, x equal to y line. Now, I hope everybody understood this. Okay. Few things about the graph is that graph can be utilized to figure out what is the work done. Okay, well, so there's a bunch of things that I need you to remember about this. Like for example, if you have something like this, okay, uh, if you have a bunch of graphs that look like this, and I ask you to find out the work done, okay, uh, what happens is when I give you a graph like this and I ask you what is happening to the work done, uh, sometimes you look at the slope of this graph and you're tempted to say, "Ki, sir, this work done is decreasing. Work done is negative because the line is coming down." But it doesn't really matter what is happening to the line, brothers and sisters. The work done value will be given by this shaded area, which is the area under the curve. And to know whether the work done is positive or negative, all you got to check is when the process is happening from A to B, is the volume increasing or decreasing? Here you can see as the body goes from A to B, the volume will increase. Okay. The slope may be decreasing, but we don't care about the slope, children. We want to work done, whether it's positive or negative, will be defined by whether the volume is increasing or decreasing. So you look at the corresponding values on the x-axis and tell me whether the volume is increasing or decreasing. Here also you will notice if the body is going from A to B, right? Then again you see that the volume is increasing again. So that means in both these scenarios, the work done will be positive. Then when will the work done be negative? Well, this is when, one second, I'll post the graph. Okay. This is how it will look like. Okay. This is how it will look like. If you have a scenario jahan pe, you know, uh, the body is going from A to B. Okay. Here you can notice that the corresponding values for volume, like volume A to volume B, the volume is decreasing. So without looking at whether this thing is line is going down, line is going up, I just can say keyword then is negative, right? Here also you can see if the body is going from A to B, the corresponding volume A to volume B is going to be decreasing. So at the end of the day, what I'm asking you to do is whenever you have a process in the graph and you want to know the work done value is positive or negative. See, finding out work done is really easy because you all of you know how to find out the area of a triangle and the area of a rectangle. So something like, or if you're good at math, you also know the formula for trapezium, area of a trapezium. This is a trapezium. Okay, there are two parallel sides, one height and one slanted, right? So you can find out the area under the curve pretty easily. The problem will be how to know whether this is a positive value or negative value. And some people accidentally look at the slope of the line. Do not look at the slope of the line. You just have to figure out in this process whether my volume is increasing or decreasing. So if you have an expansive gas, the work done would be negative. If you have a contracting gas, the work done will be negative. Okay. So that's all you have to remember about finding out work done. But there is this occasional thing where you will be asked to find out the work done in case of cyclic processes. Now, what is cyclic processes? Cyclic processes are when, okay, one second. When you have the same starting point and the same end point. Okay. What do I mean by that? Processes like these. Okay. Here you're starting from the same state and your final state is exactly the same. So if I try to draw it here, so this is, let's say, A, then you're going from A to B, B to C, C to D, and then D to E, and then back to A. The moment you realize you have a process where starting point and the end point are essentially the same, it is known as a cyclic process. How do you find out the work done in a cyclic process? Well, you can test this out. Like for example, let's say here we go from somewhere like A to B, B to C, C to D. Now here, if you find out the work done from A to B, it will come out to be this much, like the whole thing under the curve. Okay. Okay, let us use blue color so that I can match the design that is in the slide already, right? So this is going to be the work done, not inside the curve, like the entire thing will be the work done on the process AB, right? But when you find out the work done from C to D, it will be the exact opposite, but the same value. So this portion, the shaded portion right below this will get cancelled out. Okay. So the only remaining work done will be whatever is inside the figure. Because see, A to B work done may include hoga, but when you're finding out work done from C to D, this thing will also have like the same work done, but with a negative sign. Because you can see A to B is like contraction, C to D is like what is it? It's a expansion, so they will cancel out. So in a cyclic process, the work done will always be the area inside the closed figure, right? Now, in case you get like a rectangle, finding out work done is really easy. It's just do L into B. Okay. Work done in the process is B to C and A to D, by the way, are zero because these are isochoric processes. Okay. And one statement just I need you to write down in your copies is the fact that the work done is equals to the area inside the curve, inside the closed curve. Okay. Now, here, if you notice, C to D, you have like a positive work done, A to D, you have negative work done. So whatever process is on top is going to define the direction or the positive sign or the negative sign. Okay. So you can remember this. If you have like an anti-clockwise process, work done will be negative. And if you have a clockwise process, you will have positive. Because apart from the magnitude can be found out by just finding out the area inside, right? But if you want to also know whether your work done is positive or negative, just remember the sign convention. Anti-clockwise is negative and clockwise is positive. And the reason for that is also very, very simple, right? Here you notice that the subtraction will happen, so I don't have to worry about the subtraction. So whatever work done, whether it will be positive or negative, will be decided by what is happening on top, right? So A to B, you see a contraction, so that is why the work done is negative. Here also, see the bottom part, work done by these processes B to C, C to D, and D to E will anyway get cancelled out. They will get cancelled out with the work done by the processes on top. So on the process E to A and A to B, you can pretty much notice the volume is increasing. The volume is increasing. That means what? The work done will be positive. So that way also you can remember. But I suggest using this clockwise positive and anti-clockwise negative for physics. Okay, so this is all about cyclic processes. Okay, and that is pretty much the end of today's theoretical lecture. I wanted to know all of these processes and how to make the graphs and all that stuff. Okay, anything remaining in this? Let me just quickly cross check if I left something. I don't think I did. Okay, I have explained every bit of it. Now let us see if we can do questions based on this, because only knowing the theory is never good enough. Okay, so I have a few questions. Hmm. I have a few subjective questions, if you like. Like, for example, this kind of question. See, the NCRT is, do not, I'll keep telling you this, do not underestimate NCRT. NCRT is one of the greatest books if you want to, clear these exams, because uh, they work on your basic concepts, and basic if you work on your basic concepts, you're never wasting time. So stop giving me this excuse saying ki NCRT is what, it's below me. Okay, I'm too good for NCRT. If you're thinking like that, then you're not doing justice to yourself. Don't be like that. Don't be noobs. Okay. Give NCRT the proper respect it deserves. It has been made by one of our best scientists. Okay, they sat down and decided to write a book for 12th standard kids. So obviously it is difficult to understand. Just because it's difficult to understand, you'll try to diss it. That is not okay. Okay. So take up all the examples, solve examples in the NCRT. That is your starting point, right? Something like, what is the difference between adiabatic and diathermal walls? Uh, this is a question from NCRT. Little bit of subjective questions I'm giving you. You can try this at home. This will be in the slides. Where you can find the answer to these questions are also given below. So write and explain the zeroth law of thermodynamics with diagrams. Give example. Again, you can find this on NCRT page number 305. Okay. If you don't have an NCRT, get it downloaded. But I don't know why you will not have an NCRT. You're supposed, you're 11, 12, 11 kids, right? You're part of a school. And yeah, you're from Bangalore. So I think you have the money to buy NCRT as well. It's a cheap book. Okay. So, but if you don't, then you can always download it. Okay. So these are the questions. Explain the difference between heat and internal energy? It's a very good question, right? What is the difference between heat energy and internal energy? Most of the students who don't work on the basic fundamental theory, they will think that heat and internal energy are pretty much the same thing, right? If heat comes in, internal energy increases. If heat goes down, internal energy decreases. But if you talk about this first law of thermodynamics, where you say Q is equal to U plus W, then you know ki Q and U are not the same, because you can have some amount of heat like 100 joules comes into the system, and the internal energy could rise only by 50 joules, where extra 50 joules was work done by the gas. So you can't say ki heat and internal energy are similar. They are not. They are completely different things. Heat energy is like the energy transfer that is happening between different bodies, whereas internal energy is a measure of the absolute temperature within the body, which is like the kinetic energy and the potential energy of the molecules themselves at the molecular level. Okay. What is the first law of thermodynamics? I think all of us discussed in pretty much detail what first law of thermodynamics is. Q is equals to U plus W. Mention the sign convention. I'll mention the sign convention. Q will be positive if heat is coming to the system. Heat is coming into the system. Okay. And you will have Q equals to negative if heat is leaving the system, right? Because from our perspective, we are saying that whatever heat comes into the system is utilized as internal energy and work done, right? So for us, Q will be positive. Q equal to positive would mean that heat is coming into the system, and Q equals to negative would mean heat is leaving the system. Now again, W के लिए work done is positive. Work done is positive. For expansion, we just discussed in so much detail what these are, and work done is negative during contraction. This is the sign convention in physics that we follow, right? And U का तो कुछ sign convention होता नहीं है. U is just dependent on NCV delta T. So if your temperature is increasing, then U will be like delta U will be positive. If temperature is decreasing, delta U will be negative. So don't have to worry about that. But anyway, these are the kind of questions that you should at least look at least once. Okay. Uh, then you have other subjective questions where second this is another question that you can practice. One second. So you can find out the work done because of all these processes like separately. Okay. And yeah, rest of the subjective questions, I don't think if you do these many questions also, then you have a great start. So isochoric processes के लिए what is work done? Work done is 0. Isobaric के लिए work done is P into delta V, or which is also equals to nr delta T. For isothermal process, work done is what? nRT ln V final by V initial, or I can say this is equals to nRT ln P initial by P final, right? And adiabatic process would be work done is equals to minus NCV delta T. So these are the four formulas that you have to remember when you're doing questions. Okay. Now, NCRT questions, enough of NCRT questions. I think everybody will be, how can I say this? Comfortable by now. Okay. Now let us see if I can do some J mains level. Okay. Uh, and the best source of any questions is the mains themselves. I mean, you could get the best author book, and I would still say these questions are better than them, because a author will use his own whims and fantasies, right? But the best way to prepare for an exam is to check what the exam asked in the previous year. What could be better, right? So this is the main 2019 question, which I think all of you will be able to do if you put a little bit of effort and if you paid attention during the class. So please try, go ahead. I'll put a 5-minute timer on this. Okay. And please let me know if you have any doubts in all of this. So I'm running the timer right now. So 5 minutes on the clock. Think and let me know. Okay. So 5 minutes have started. I'll be back in 5 minutes. Please go ahead and try this and let me know if you find the answer. Yes, children. Anybody found the answer? I don't see anyone giving me any chat answer though. Come on, guys. I need you to answer this question. I think you can. Okay, I'll help you. Gas is taken from A to B. So that means my process is starting from A right here, right? Let me zoom in if this is not big enough. Is that the reason people didn't find the answer? Because it is not big enough? Okay. So this is my body A. It is going from A to B. Okay. A to B. So this is my initial point, this is my final point. We are two different processes. So one is going from like A to C, then C to B. And then there is other process where it's going from A to D and then D to B. Notice in this kind of questions, whenever you have like multiple different processes, my mind is just ringing this. Delta U will be same, delta U will be same, delta U will be same. So that alarm should also go off, right? So whenever you have multiple processes, different paths, the one thing that you can rely on is the fact that the change in internal energy in both these processes are going to be exactly same, right? So when you go through ACB, they're saying during this ACB process, so let me list this down. In ACB process, what I'm going to do is I'm going to write this table Q and then U and then W, because these are the only three things that I'm worried about. So in this ACB process, 60 joules of heat is flowing into the system. So that means plus 60 heat is given to the system, right? And 30 joule of work is done by the system. So that means this is plus 30 joules, right? And what else? What else about ADB? If the path ADB is used, work done by the system is 10 joules. So in ADB, what they have said is that the work done is 10 joules. So how much is the heat? That is the question. My God, it's a mains question, guys. It's easy. You can easily crack JEE mains if you pay little bit of effort. If you put little bit of effort, you can do JEE mains, because and thermodynamics, let me tell you, thermodynamics is my highest priority when I was studying, is because it's there in two subjects and it's a pretty big chapter. So if you're done with thermodynamics, you have three chapters in your whole in your 11th physics, and pretty much one big chapter in chemistry as well. So it's like huge weightage. Even when I'm starting the revision for the 12th program, which you will be attending next year as well, there also you'll notice me starting with thermodynamics first, because it has the huge uh, weightage, and it's not very hard. At least you don't have to imagine fancy level like rotation mechanics. You have to think about the questions a lot, but here you don't have to do that. But anyway, now in here, again, I see that delta U is going to be same in both the scenarios. So it is vital for me to find out in the first process. I write Q is equals to U plus W. So from here, Q is 60, U is, I don't know, and 30. So from here, U also comes out to be 30 joules, right? So this is 30 joules. But immediately, I also know that it is 30 joules for the other process as well, because their initial and the final points are same. So if I use the first law of thermodynamics for the second process, I'm going to write Q is equals to U plus W again. This time Q I do not know. U is 30 and work done is 10. So your answer will be 40 joules. So that is the correct answer for you guys. Okay. So this is the work right there. So if you have any doubt, again, feel free to ask, uh, and then let me know. Let me know. Okay. So this is one of those easy peasy lemon squeezy questions. Okay. Let's graduate into slightly more and more difficult I'll make with each time. Uh, Let me ask you something like this. 1 second. 1 second, guys. I'm just opening the PYQs, and I'll be asking you directly from PYQs. What better to practice from than a book PYQ book? Okay, so there's nothing better, to be honest. By the way, if you don't have a PYQ book, you can buy one. The uh, author does not matter, because PYQs are PYQs. So you can either get it from the Arihan publication, Disha publication, any kind of publication. PYQ is good enough, right? So uh, yeah, that is good enough. So let me open one physics PYQ book. Why can't I find one? Found it. Mm-mm. I have the Disha publication one. You can, again, you can use any one that you like. Back cover, back page, contents. Gravitation, mechanical properties, thermodynamics. Found one. Sorry, I'm taking a little bit of time to open this. Actually, didn't know where it was, which folder it was. Sorry. So I have the PYQ with me. So I'm going to share my screen with you. This is how the PYQ looks. If you don't know, this is how the book looks. First law of thermodynamics, we have a bunch of questions. I think we did this one right now. Question number 8, I think we just did. Let's do some more. Let me take this question with us. It's a graph looking question, and graph makes it a little bit, people find the graphs a little bit, difficult, a little bit teasing. So let's see if we can solve this. Uh, okay, so here is the question. Let me share my whiteboard with you guys. This is question number 4. Okay, again, I'll give you 4 minutes to 5 minutes to try yourself. Okay, and then I'll explain. Okay, so your timer is running 5 minutes, and I will explain. Okay, guys. This is again a 2023 JEE Mains direct question. I think we can solve this very easily. Okay. Notice that they are saying the pressure of the gas changes linearly with volume from A to B. So this is important to me. Although arrow is given, but it's very vital to know where the what is happening to the uh, what is the direction of the process. That will matter a lot. Okay. Now, as soon as I see the arrow, I can see that volume wise, this is changing from 200 cc's to 50 cc. So that means the volume is decreasing. So that means work done will be negative and all that stuff. So I know this is a compression. At least I know that much, right? Next thing they're saying ki no heat is supplied. Oh, this is good because if I understand Q is equals to U plus W, right? And I am saying that Q is equals to 0, then one thing I can understand that delta U will be nothing but negative of work done. right? Because at the end, they're asking change in internal energy, which means indirectly they're asking us what is work done, right? Or what is negative of work done. So let us first find out what work done is. Now I said in a PV graph, the work done can be found out. This is volume, by the way. Okay, volume, pressure versus volume graph. Work done is found out by finding out the area. Now what I'm going to do is make a line like this. I believe this is 10. Okay. So this is a triangle whose area will be what? Area of a triangle is given by half into length into breadth. So the work done in that triangle will be half into length. Now length is how much? This is going from 50 to 200. So 200 minus 50 is 150 cc, centimeter cube. Now if I want this to be in standard units, then SI units, then centimeter cube, if I want to convert into meter cube, I have to multiply with 10 to power minus 6. Okay, this is length. And how much is half into base? So this is base, 150 into 10 to power minus 6 is the base, like this distance from here to here. And the height from here to here will be how much? This height will be how much? Well, it is going from 50 Pascal, 10 Pascal to 50 Pascal. So the height is like 40 kilopascal, so 40 into 10 to power 3, right? Now, if you try to solve this, and by the way, this is the area of the triangle. This is the way work done under the triangle only. So this will be like what? This will cancel out, will become 10 to power minus 3, right? And then you have 15 times 4, that's 60. 60 and two zeros, that's like 6,000 by 2. So it's like 3,000. Okay. So that's like 3 joules. 3,000 into 10 to the power minus 3 is just 3 joules. Now let's talk about what is the area of this rectangle, because the total area under the curve will be the total thing. So I also have to add this area of the rectangle here. Okay, which will be nothing but length into breadth. So again, this is like what? 150 into 10 to the power minus 6, right? And the width of the rectangle is just 10. So 10 into 10 to the power 3 pascals. Okay. So that's like what? 1500 into 10 to the power minus 3, which is like 1.5. Right. So the total work done is 4.5 joules with a minus sign. Why did I put a minus sign in front? Because I know volume is decreasing, so work done will be negative, right? Work done will be negative. Now, what will be change in internal energy? It's negative of work done. So, which means negative of negative 4.5. So, your answer will be like plus 4.5 joules. Okay, so I hope everybody understood. If you have any doubt on whatever I explained, please let me know. Please let me know if you didn't understand any part of this. Okay. Okay. No doubts. Then let's do one more question on first law of thermodynamics, and then we'll do some other question. Okay. So again, look at the ease with which you can do all of these questions. Like for example, this question also. Look at this question. So easy this is. This is from 2023. So last year. Oh, this year. Sorry. Sorry. This year. This year, April 6th, this question came in JEE Mains, and believe me, question like this that can bring you rank. Minimal efforts on understanding, lot of practice, knowing what to prioritize will get you good marks. The source of supplies, so it is supplying heat to a system. So heat is given to us as like plus 1000 watts. Like this is not actually heat, this is like power. So it's like heat cube by time, right? Then system performs work at a rate of 200 watts. So they are saying that work by time is what? 200 watts. My God, they are asking what is the rate at which internal energy of the system is increasing. My God, can it be easier than this? They're just asking you to do a subtraction, guys. They're asking you to find out, okay, Q is equals to U plus W, and heat is coming to the system, so it's like 1000 watt. System is doing the work, so it's like plus 200 watts. So it's like 1000 is equals to U plus 200. Oh my God, can it be easier than this? So U is how much? Come on. Actually, delta U by T. Okay. So the only thing was ki you divided the equation by time, and that's what the rates were talking about. Nothing but the same time. So it doesn't do not have to even worry about the time here. Okay. So you just understood that the change in internal energy per unit time would be like 800 watts. As easy as this, guys. This came this year. So think about it. If you pay a little bit of attention, a little bit of effort you put in, you can create great results in JEE Mains and JEE Advanced. Okay. Now, let us do some slightly tactical questions, which means we'll be looking at questions that involve adiabatic process, right? So let's see if we can do this. Okay. I hope you remember what uh, bulk modulus is. This is on the slightly on the higher side. Okay. So I showed you the easiness of this exam, but there are also some difficult questions in the exam itself. Like this is again from that same exam, and this one was slightly more difficult. But again, people who are unable to read this part, this word is temperature is equal. This is equal. This word is equal, and okay, and the rest of the question is same. So this is temperature. Okay, so go ahead and try this question. Now, people who forgot what bulk modulus is whatever is the change in pressure divided by change in volume by original volume. Bulk modulus is like the modulus, or also with a minus sign, if you remember. Change in pressure divided by change in volume by original volume, like delta P divided by delta V by V. Volumetric stress by volumetric strain was known as bulk modulus. So what you have to find out is this one, okay? And it is given to us that P into V raised to power 3 is equals to constant. By the way, this is not an adiabatic process. I am planning to take some questions from adiabatic process, but this is not one because 3 is not an adiabatic constant. So again, I'll give this one is a slightly difficult question. So again, I'll give you 5 minutes to try. Okay, your timer has started. 5 minutes on the clock. You guys need a hint? I can help. Okay, guys, 5 minutes are up. I'm going to explain this. Okay, so how you do this question is pretty much simple. Okay, so I need uh, what do I need? I need what is change in pressure, what is change in volume by original volume with a minus sign, right? For small changes, the delta can be written as like so. What I can do here is I can differentiate this equation both sides. Okay, it's given to us that p into some constant into v raised to power minus 3. So I have written it like this: p into v cube is equals to constant. Now, if I differentiate this side, I have two variables. Now, if you remember, uh, this is how you differentiate. Like if a and b are multiplied together, this is how you differentiate. I don't know if you remember this. Okay, but I taught this in your bridge course. If you haven't done the bridge course, I highly suggest you to. The videos for this is available on Learners. You can do little bit of basic calculus is required, where I teach you how to multiply two quantities if they are how to differentiate these two quantities if they're multiplied. So the formula goes like this: if you have two things, then you first write a as it is, differentiation of the second, plus second as it is, differentiation of the first, right? So let us differentiate this. Let's say I'm doing it with respect to x only. So I'll write something like p into 3 times of v squared dv by dx. Now this is the different, this part is the differentiation of the second on the left hand side. Okay, plus v cube as it is, and then you have like dp by dx. Differentiation of p with respect to x will be like dp by dx. It won't be 1. Differentiation of x with respect to x is 1. But if you're differentiating p with respect to x, and it will be, so this, all of this will be equal to 0. 0 because you're differentiating constant on the right hand side. Differentiation of a constant is 0, right? So what you can do is get rid of this dx sign as well, because on the other side, you can take dx and then take it to the other side, right? So v square will cancel out with the cube. And what I'm going to do is rearrange the terms. I'm going to write something like 3 times of p dv will come out to be minus of v dp. I just took this particular term to the other side of the equation, right? So this becomes minus v dp. Now look at what I'm trying to find out. Okay. So okay. So if I rearrange this term one more time, I can take dv to the other side, and this will be what? 3p 3p will be equals to minus v dp divided by dv. And this is what, this is the bulk modulus we were looking for. This is the bulk modulus that we were looking for. Okay. So only like, look at this, 1, 2, 3. Only 3 steps it took for me to solve this. But again, I understand this conceptually a little bit on the higher side compared to other questions in the JEE mains. But again, if you have a little bit of knowledge of differentiation, which you will be very comfortable with by the end of the year, because your math teacher is going to teach you specifically differentiation. So this kind of differentiation will become very easy for you later on, right? But this is how you solve this question. Again, please, if you have any doubts, feel free to ask. Okay. Okay. I have another question. This is a graph-based question. Again, all of these questions, I'm taking up latest questions so that this remains relevant. Discussion becomes relevant. What better to see the question that came this year only? Serious guys. Okay, guys. Again, this is one question. If you paid attention to the simulation that I showed, it is very easy for you. Okay. Now I have put this equation, and if you remember, I put this x equals to c in the Desmos calculator. And if you remember, this is how the graph looked like. I still have it actually. Let me share the screen with you guys. Uh, where did it go? Yeah. If you remember this, okay, let me share my screen with you guys. This is how the graph looked. Okay, look at this equation. Xy equals to C, and the value of C you can adjust. Okay, so if the value of C increases, the graph goes away. It goes away from the origin. Now, as you bring the number closer in, it approaches. Look at this 0.3 mate is so close to origin, but as you move the number up, it goes further and further away from the origin. Okay, so if you know this property, if you know this property, I'll tell you how to solve this question right here. So the part here that you will be worried about is, you guys know ki B and C option are incorrect because it's saying isothermal, right? So that means it has to be like a hyperbola. But they're also saying that T3 is greater than T2 is greater than T1. So that means either D is correct or A is correct. Now, what do you think is correct? Right? Now, as we know that actually pressure into volume is what? nRT. So if you increase the value of C, that means your PV will be like a bigger constant for higher temperature. So it will be further away, right? So T3 being the highest means that T3 ka graph will be like the furthest distance away from the origin. So in that case, D is the correct answer. Okay, so D is the correct answer. That's how you do this question. Again, please let me know if you have any doubt in this question. It is a very beautiful question. Again, little bit of math, little bit of physics, and we are good to go. We are good to go. Okay. So very application based question. So easy this year's J Mean Physics. Okay. Now let's do one question integer type. This is from 2020 to 2021. Okay, so let's see if we can do this question. Okay, this is an integer based question. This is the question on the screen. Okay, let me explain this question to you guys. This is going through a cyclic process. Cyclic process means if it's starting from A, then it goes and comes back to the same position. Right? Now, there's something good about these cyclic processes that delta U in these kind of processes will always be zero. And the reason for that is because, again, like I said, delta U is what? It's a state function. It's a state function. It does not depend on path. It only depends on what is the initial temperature and what is the final temperature, right? So if you're starting from the same point and you're ending at the same point, that means your initial and final temperatures are same. So delta U for cyclic processes will always be zero. Now this would mean Q is equals to U plus W wala equation mein, which is like the first law of thermodynamics. Q will be equals to W, right? So the question which is asking what is the energy absorbed, indirectly they're asking us how much is the work done, right? How much is the work done? Now I said in closed figures, all you need to do is find out how much is the area, right? Now, to find out the area of a circle, you're going to say that is equals to pi into r square. But how much is r? How much is the radius? Well, here you understand that your value is like what, 20. This right here is what, 20 kilopascal. Okay. So 20 kilopascal would mean ki 220 into 10 to power 3 pascals. 20 into 10 to power 3 pascals. Okay, which means it will be 20 pi r square. So, okay, this is going to be fancy. Hmm. Okay, let me check the answer if this is correct. I feel like this is wrong. Question number 32. The reported figure. I feel like this question has some issues with it. Don't feel like the see here because it's said in liters. You have to convert. If I convert into standard units, this will be like 20 liters, which is and we know that 1,000 liters is like 1 meter cube. So 1 liter is like 10 raised to power minus 3 meter cube. Okay. So 20 liters will be approximately 2 into 10 raised to power minus 3 uh, meter cube, right? But if you see on the other side, this is so in that case, this will not be a circle, no? Because this on the left hand side, you have kilopascal. And on the but if you multiply them, so it's like 20 kilopascal into 20 into 10 to power minus 3 meter cube. So 10 to power 3 and here 10 to power 3 cancels. So it is like 400 joules. It makes sense. Okay, now it makes sense. So I don't have to worry about these units because if I multiply them, the answer is like 0. So all you have to do is worry only about the values. So it's like 20 on this side, 20 on this side. So makes it a circle. Yeah, perfect. This is perfect. Because what I was worried was this width was like 20 into 10 to power minus 3 and this is like 20 into 10 to power plus 3, so it's not even a circle, but I don't have to worry about them because when you multiply these two quantities, I am getting the answer in joules. Here you can notice the answer is given in joules, right? So don't have to worry about that because it's the units will anyway cancel out. So it is a circle with radius 10, right? So here it will be just what 10 square, so 100 is my answer, right? So your value is pi into 100 because area for the circle is like pi r square. R is 10, so you have like pi into 100. Okay, so that will be your answer. So 314 joules approximately is going to be the answer. I think we can squeeze in one more question because I have uh, what you call 5 more minutes for you to be able to do this. Okay, let's do a nasty question. Let's do a nasty questions. Okay. So this one is a little bit nasty. 2020 में this came. Okay. Requires a little bit of understanding of the how the graphs is going to work. So let us explain this. Okay. So the last question for today's session is from 2020. It's slightly on the trickier side, but I want you to try it nonetheless. I think you can do it. 5 minutes on the clock. I'll explain in 5 minutes. Okay, guys, let me explain this. Which of the following is an equivalent cyclic process corresponding to the thermodynamic cyclic given in the question? So A to B, oh, okay, 1 to 2 is adiabatic. Okay. So this is a PV graph and A to 1 to 2 is a adiabatic process. Okay. 2 to 3, they don't have to say, but I already know 2 to 3. So 1 to 2 is adiabatic. 2 to 3 is what? It's a isobaric process. How do I know this? Because it's a horizontal line. Horizontal line in a PV graph means that pressure is remain constant, right? And 3 to 1, guys, is what? It's a isochoric. Okay. So this means that PV raised to power gamma is constant. Isobaric means P is equals to constant, right? And this one is V equals to constant. So if I try to write the equations for it, this is how it will go, right? Now, the graph that I have to transpose this to is it's a velocity versus time graph. No, it's not. It's volume versus temperature graph. Okay, they haven't said it, but I think from the context you have to understand that V is not velocity, T is not time. Okay, so it's a volume versus temperature graph. Okay, now in volume versus temperature graph, if volume is constant, so 3 to 1 wala process jo hoga, the 3 to 1 process will be a horizontal line because volume has to remain constant, right? So which of these will have 3 to 1? So if you look from 3 to 1, this is a possibility. 3 to 1, here also it's a horizontal line. This is also a possibility. 3 to 1 is also a horizontal line. This is also a possibility. D is not a possibility is because you can see it 3 to 1 process looks like a curved line, and that is not correct because 3 to 1 is a isochoric process. Second thing, if I say that pressure is constant, if I say pressure is constant, then using this equation, PV equals to nRT, PV equals to nRT, you will realize if pressure is constant, then I can write volume is equals to some constants into temperature. So which is like saying if Y is equals to some constant into X, right? So that means for this second process right here, 2 to 3, has to be a straight line which will be like coming from the origin. It'll look like it is coming from the origin. So it's like 2 to 3 should be another straight line that is coming from origin. Now look at this. 2 to 3 is a straight line. Straight line, I'm not saying horizontal line, I'm saying straight line coming from origin. So B is something that I can cancel out because if you think about it, B to 3 is a curved line. So that means B is also not an option. B is also not an option because B to 3 is supposed to be a line coming from the origin, but this is not even a straight line is not coming from origin also. So again, I'm stuck between A and B. Now, P V raised to power gamma is constant. If I think about this, okay, I have to find out the relationship between if I say P into V raised to power gamma is equal to constant, I told you that this can also be written as temperature into volume raised to power gamma minus 1 is constant, right? So you know that this is not going to be a straight line because how will this be a straight line? This is to the power of something. Straight lines may Y should be some constant into X plus C. This is the standard equation of a straight line where Y should be power 1, X should be power 1. Here you can see that my X axis quantity is power 1, but my Y quantity is not raised to power 1. It's a decimal, right? So it has to be a curved line. So my answer will be C. A will also not be an option because 1 to 2 they are showing like a straight line, which is not correct. Okay, so that's how I know that the correct answer is going to be C. Anyway, that is the end of today's lecture. Thank you for being here. I need you to be a little bit more participative. I didn't hear a single sound in this class. So yeah, I hope everybody is studying on the other side of the screen though. But anyway, uh, best of luck. Keep preparing. I'll send you the notes and a recording as well. But the recording goes away after some time. So be careful. If you want to download it, you can quickly download it as soon as I post it. Like it takes 1 hour to process, and then after that it's available. So by evening, please download it if you want to watch it again or something. Because after that, the uh, you know lecture goes away. Okay. So anyway, with that, I'd like to conclude today's class. Thank you for being here. I will see you next Sunday, guys. Take care. Bye bye.
Thank you, sir.
Okay. Finally. Bye bye.
Thank you, sir.